In the realm of modern physics, few figures have captured the public imagination like Michio Kaku. To some, he is a gifted communicator, bringing the mysteries of the universe to the masses with eloquence and clarity. To others, he is one of the most daring theoretical physicists alive, a man unafraid to tackle the deepest questions. Where did the universe come from? Why does it have the laws it does? And can all of it, every particle, every force, every constant, be explained by a single, elegant equation? For Kaku, the answer lies in the quest for what he calls the theory of everything. A theory that, if found, would be nothing less than the mind of God. The idea is not new. Albert Einstein spent the final decades of his life chasing such a unifying framework. He believed that the apparent diversity of the universe, the multitude of forces and particles, was an illusion, and that at its heart, nature was governed by a single, harmonious principle. But Einstein died without finding it. In the years since, many have tried to pick up where he left off. Among them, Michio Kaku has become one of the most recognizable champions of the idea, dedicating his career to developing and popularizing the leading candidate for this ultimate theory, string theory. At first glance, string theory seems bizarre. It proposes that the fundamental building blocks of reality are not particles, tiny, indivisible points, but minuscule vibrating strings of energy. These strings are unimaginably small, about 100 billion times smaller than a proton, and yet the way they vibrate determines everything about the universe. One pattern of vibration might produce what we know as an electron. Another might produce a quark. The universe, in this view, is like a cosmic symphony, and the laws of physics are the harmonies played by these vibrating strings. But string theory does more than just replace particles with strings. It also unites the four fundamental forces of nature: gravity, electromagnetism, the strong nuclear force, and the weak nuclear force. In our everyday lives, these forces seem very different. Gravity holds planets in orbit. Electromagnetism powers our electronics. The strong force binds atomic nuclei. The weak force governs radioactive decay. Yet string theory suggests that all of them are manifestations of a single underlying reality, different notes in the same grand composition. Kaku often describes the beauty of this idea with a kind of poetic reverence. To him, the mind of God is cosmic music resonating through 11-dimensional hyperspace. 11 dimensions may sound like science fiction, but in string theory, extra dimensions are a necessity. The mathematics demands more than the 3 spatial dimensions we perceive, plus time. These additional dimensions are curled up so tightly we can't see them, tiny loops hidden in every point of space, influencing the vibrations of strings in ways that give rise to the laws of our universe. But here's the challenge. String theory is notoriously difficult to test. The strings are so small and the energies needed to probe them so immense that direct experimental evidence remains elusive. Critics argue that without such evidence, the theory risks becoming more philosophy than science. Kaku acknowledges this, but he points to indirect clues. For instance, string theory naturally incorporates gravity, something earlier attempts at a theory of everything could not do. It also predicts the existence of certain particles and symmetries that could, in principle, be detected in future experiments or observed in the remnants of the Big Bang. For Michio Kaku, the lack of immediate experimental proof does not diminish the importance of the quest. He argues that history is full of theories that preceded their evidence, ideas that seemed speculative until technology caught up. When Einstein proposed general relativity, the tools to test it barely existed. It was only later through astronomical observations that his equations were confirmed. Kaku believes string theory is in a similar position, a mathematically consistent framework waiting for its moment of experimental vindication. Part of what makes Kaku's vision so captivating is how he connects it to humanity's oldest questions. What happened before the Big Bang? Are we alone in the cosmos? Is the universe finite or infinite? String theory offers potential answers, though often in ways that challenge our intuition. For example, one of its implications is the multiverse, the idea that our universe may be just one bubble in a vast cosmic foam, each with its own laws of physics. In some of these universes, stars and galaxies might never form. In others, life might evolve under entirely different conditions. To Kaku, this paints a picture of reality that is both humbling and exhilarating. We are part of something far larger and stranger than we can easily imagine. But string theory's most ambitious claim is that it can reconcile the two great pillars of modern physics: quantum mechanics and general relativity. Quantum mechanics governs the very small, the realm of atoms, particles, and probabilities. General relativity governs the very large, stars, galaxies, and the curvature of space-time. These two theories have been experimentally verified countless times, yet they are mathematically incompatible. In extreme environments, like the center of a black hole or the instant of the Big Bang, their equations break down. String theory, Kaku says, is the bridge between them, the long-sought unifying framework that can describe all of nature's forces in a single language. One of the most intriguing offshoots of this pursuit is Kaku's work on the concept of hyperspace. In our daily lives, we think in terms of up and down, left and right, forward and backward, three spatial dimensions. But if string theory is correct, reality contains many more dimensions than we can perceive. Hyperspace is the mathematical arena where these extra dimensions exist, and it allows for elegant solutions to the otherwise intractable problems in physics. In hyperspace, the forces of nature are not separate. They are different facets of the same geometric structure. Kaku often uses this idea to explain phenomena that seem mysterious. Gravity, for instance, appears incredibly weak compared to the other forces. A small magnet can lift a paperclip against the entire gravitational pull of Earth. String theory suggests that gravity's relative weakness may be because it leaks into other dimensions, spreading its influence thin across a higher dimensional space. This not only explains its weakness, but also opens the door to experiments that might indirectly detect these extra dimensions, perhaps through subtle deviations in gravitational behavior at small scales. Still, the journey toward the God equation is as much philosophical as it is scientific. Kaku acknowledges that unifying the laws of physics would not automatically answer every question about existence. It would, however, provide the foundation, a single, coherent framework from which the rest of reality emerges. In his view, discovering such an equation would be humanity's greatest intellectual achievement, a triumph that would redefine our place in the cosmos and confirm that, at the deepest level, the universe is knowable. Kaku's pursuit of the God equation is not limited to academic circles. He has devoted much of his career to making these complex ideas accessible to the public. Through books, documentaries, and countless interviews, he brings the mathematics of hyperspace, the elegance of string theory, and the mysteries of the multiverse into living rooms around the world. His ability to blend rigorous physics with vivid metaphors has inspired millions to think about reality in new ways. He often compares the universe to a chessboard, where most of us learn the rules only well enough to play, while physicists seek to understand why the rules exist at all. String theory, in his analogy, is the ultimate rule book, one that explains not only how the pieces move, but why the game exists. In pushing the boundaries of physics, Kaku also ventures into the speculative territory of the future. If we can truly understand the fundamental laws of the universe, he argues, we might harness them to achieve what today seems impossible. Concepts like faster-than-light travel, wormholes, and manipulating the fabric of space-time are still far beyond our engineering capabilities. But in principle, they are not forbidden by the laws of physics as we understand them. A complete theory of everything could reveal the precise conditions under which such feats might be possible, transforming science fiction into science fact. This is where Kaku's vision takes on a dual character, both scientific and almost spiritual. He often says that the laws of physics are the mind of God in the language of mathematics. For him, this is not a theological statement, but a reflection of the deep order and harmony embedded in the cosmos. To discover the God equation would be to read the universe's source code, to see the architecture upon which all of existence is built. Whether one interprets this as divine design or as the ultimate triumph of human reason, the significance is profound. Of course, there are skeptics. String theory's mathematical beauty does not guarantee that it reflects reality. Some physicists argue that without falsifiable predictions, it risks becoming detached from empirical science. Others explore alternative frameworks, such as loop quantum gravity, which attempt to unify physics without invoking extra dimensions or vibrating strings. Kaku, however, remains confident that string theory's elegance and consistency make it the leading candidate. For him, the absence of direct evidence is a challenge, not a fatal flaw, a call to push the limits of technology and creativity until the universe yields its secrets. In this way, Michio Kaku embodies a rare blend of dreamer and pragmatist. He knows the road to the God equation may be long and uncertain, but he also knows that every step toward it enriches our understanding of the universe. Even if the final equation remains elusive in our lifetime, the pursuit itself fuels innovation, inspires curiosity, and deepens the human story. For Kaku, the journey is as important as the destination, because in seeking the ultimate truth, we become something greater than we were before. As Kaku often reminds his audiences, the search for the God equation is not just about physics, it is about the fate of civilization. The knowledge gained from unifying the forces of nature could reshape our technological future in unimaginable ways. Mastery over the quantum and cosmic scales could lead to breakthroughs in clean energy, space travel, and even the manipulation of matter at its most fundamental level. With such capabilities, humanity could become a multiplanetary or even interstellar species, no longer at the mercy of planetary disasters or the finite lifespan of our sun. Yet with such power comes an equal measure of responsibility. The same understanding that could enable interstellar travel could also create weapons beyond our current comprehension. Kaku warns that every great leap in human knowledge has been a double-edged sword. Fire warms and cooks, but it also burns. Nuclear physics gave us electricity, but also the atomic bomb. The God equation, if found, would be the sharpest blade yet, a tool that could elevate humanity to cosmic guardians or doom it to self-destruction. This is why Kaku emphasizes that the pursuit of ultimate knowledge must be paired with wisdom. Science, he insists, is not merely about acquiring facts, but about understanding the consequences of those facts. He envisions a future in which global cooperation and ethical responsibility match our technological ambitions. In this vision, the God equation would not be the property of any one nation or corporation, but a shared legacy of humankind, a map for building a future that honors both our curiosity and our survival. Perhaps the most inspiring part of Kaku's message is his conviction that we are capable of reaching such heights. For all the challenges, political, economic, and existential, he sees humanity as a young species just beginning to grasp its place in the cosmos. If we can avoid the traps of short-term thinking and narrow self-interest, the next few centuries could mark our greatest era, the time when we learn the ultimate laws of nature and use them to transcend the boundaries that once defined us. In the end, whether the God equation is discovered tomorrow, in 1,000 years, or never at all, Kaku believes the pursuit itself is one of humanity's noblest endeavors. It is a journey that forces us to confront the deepest mysteries, to innovate beyond the limits of imagination, and to unite in the shared quest for understanding. And perhaps that is the ultimate lesson, that the meaning of the universe is not just hidden in the final equation, but in the act of seeking it together. Michio Kaku's quest for the God equation is, at its heart, a story about the human drive to know. From the moment our ancestors looked up at the night sky and wondered about the stars, to the present day where we wield particle accelerators and space telescopes, we have been chasing patterns, threads that connect the chaos of existence into something coherent. Kaku stands in this ancient tradition, but with tools and insights that those early stargazers could never have imagined. For him, physics is not simply a profession, it is the language in which the universe writes its autobiography. One of the most compelling aspects of Kaku's work is how it blurs the line between science and philosophy. When he speaks about extra dimensions, multiverses, or the ultimate fate of the cosmos, he is not only presenting equations, he is inviting us to consider what they mean for our own place in reality. If string theory is correct and we live in a vast multiverse, what does that say about the uniqueness of our world? If time and space are emergent properties rather than absolute, what does that mean for concepts like destiny or free will? In Kaku's hands, physics becomes a bridge to questions that have traditionally belonged to poets, theologians, and philosophers. Kaku also understands the importance of imagination. He often says that today's science fiction is tomorrow's science. The warp drives, teleportation devices, and parallel worlds of literature and film are not just escapist fantasies. They're thought experiments, ways of stretching the boundaries of what we consider possible. By encouraging people to dream boldly, Kaku believes we create the mental space in which scientific breakthroughs can occur. After all, many of today's technologies, satellites, smartphones, even the internet, were once the stuff of science fiction. But perhaps the most powerful thread running through Kaku's vision is hope. Despite acknowledging the dangers of advanced technology, he consistently frames the future as a realm of opportunity rather than doom. The God equation, if found, would not be an ending, but a beginning, the foundation for a civilization that could explore, create, and thrive on a cosmic scale. It is a vision that refuses to accept the limitations of the present and instead looks to a horizon where humanity has mastered not only the laws of nature, but also the wisdom to use them well. In this way, Michio Kaku's work is more than the pursuit of a single, elegant equation. It is a call to expand our minds, to embrace both the rigor of science and the wonder of imagination, and to recognize that the universe's greatest mystery may not just be how it works, but what we choose to do with that knowledge once we understand it. In the end, Michio Kaku's search for the God equation is not just about unlocking the mechanics of the cosmos, it's about unlocking ourselves. It's about proving that a species born on a small, fragile world can rise to comprehend the deepest truths of reality. Whether the final answer is written in the vibrations of tiny strings, the geometry of higher dimensions, or something we have yet to imagine, the journey there will redefine what it means to be human. And perhaps, when we finally hold that equation in our hands, we'll realize that the real power was never in the formula itself, but in the courage it took to seek it.